Hi, my name is Alex, and as I was preparing for an interview, I got to understand that I'm not sure exactly how the inference part of LLM model works. So I was trying to understand it by searching and looking at a few videos online, interacting with LLMs itself, and trying to get it to understand, get myself to understand it. And I think I didn't manage to do it for some time, but then after spending a lot of energy and putting a lot of energy into it, I think I got a mental model for myself that I think I understand, or that helped me understand. And in this video, I'll try to present the same mental model that I built for myself and how the inference part works. Like basically, like life of a prompt. What happens after you input a prompt into the text editor, or in ChatGPT or in Gemini, whatever, and what happens until you get out the response. And I'll share with you the mental model that I built for myself, while I walk you through all the stages. So let me share with you the diagram that I have. This one. Yeah, cool. So we'll start from here, from the left, and go to the right. And I will use the steps that are familiar with us as a user, which is you write in the prompt and then you press enter. And now seconds later or milliseconds later, you get out the response that builds in front of your eyes. So the first thing is we have the prompt, which is a collection of words in sequence. And LLMs use tokens, and tokens are slightly shorter subwords. And the reason why LLMs use this is I think I'm not an expert on that part yet, but I think it just creates more um, kind of um, balanced way of like looking at the subwords, so that you don't have different lengths, and they're all well aligned. And I think that might be part of the reason. I think as you dive deeper into the subject, there might be better explanations to this. But you can, for the purpose of this, you can also think of those tokens as being words, but just know that they are actually smaller sub parts of the word. Okay, so you have the prompt, and the first thing, it gets chunked into those tokens. And the reason is LLMs have a dictionary that transforms those tokens into a numerical vector-based representation of them. And the analogy that I would start using here is, think about like the words and you having a dictionary, and you have the word, and when you look it up in the dictionary, it kind of explains to you what that word means and all its meanings. Uh, that's sort of the way I see it. Is not 100% accurate, I guess. But that's how that's the mental model I created for myself, right? I look it up, like for every token in the prompt, I look at the LLM model, kind of pulls in the vectors that describing that token, or if you think about them, words, that word. And first, one thing that I want to clarify, it took me some time to understand when I got into this, is why it actually is that this AI models use vectors, and why do we go from words or tokens into math, into like a numerical vector-based representation. And I think for this, the way I got to see it, again, I'm not sure if this is the best way to describe it, but it's the way it helped me understand, is you can think about like when you see two words, for example, in the dictionary, their characters don't mean anything for us that would help us understand if those two words are similar, right? The way we as humans compare two words to understand if they are similar is by looking in the dictionary, and then based on the definition of the word, we're trying to assess similarity. But it's not based on characters, right? You're not comparing two words character by character and trying to figure out if they mean the same thing. Actually, you're going to the dictionary and comparing the understanding of that of those two words. And I think it's kind of similar here, because you go from token into those vectors that describe what the token means, because you want them to be able to do computation that would be something like, okay, given two tokens, how similar they are. Because if the vectors kind of point in the same direction, like that gives you an idea that maybe those two tokens are kind of similar, right? And we'll get into this also a bit later. Okay, but that's an analogy, right? So in order to do this computation, you're going in from tokens and into those vectors, right? Like now, for me, it was useful to know that, okay, for every token that I have in my prompt, I will have a vector, like multidimensional, maybe 4096 float values per token. Okay, so that's the setup part. That's how we start here. And now I want to go back to the original prompt that we're starting with. You have a prompt, and what LLMs are doing is they want to be able to compute the next the next token that makes sense. So based on your prompt, all the computation is geared towards helping LLMs figure out what's the next token that would fit after your prompt. And in order to do that, if you think about it, you're having a dictionary. You already have a dictionary of possible tokens, right? So you need to choose among one of those. Now the question is, which one is kind of relevant among all the ones in the tokens for the prompt? And for this, we are going into this whole computation that we're gonna discuss. But that's what we ultimately want to reach, a point where, based on the prompt, we have a vector or something that would help us decide among all the possible tokens that are in the dictionary which one to choose, right? And kind of sort them. Okay. So now that we established what we're trying to do, the way the second phase works is we're starting with this. We can think about them as on a per token basis, right? So think about one token in your prompt, and this happens for all of them. But for one token in the word, there are a few layers that transform this token or this vector, right? Basically, what it's trying to do is trying to bring the meaning of the token, or of, yeah, the meaning of this token. It wants You want to enrich it so that it is the actual meaning that the word or the token has in the prompt, right? Because the words have, as you know, they have all this like all the different interpretations. They can mean different things. You want, and the thing that this transformer layers are doing in different ways, but they are all trying to get the vector for that token to be as close as possible to the actual meaning of the meaning of the word in that context. Okay, cool. So now, so we have a few, like we have maybe 96 different layers, right? And in every layer, you get the token in, you get the token representation, the vector in, and it does a lot of computation that tries to move this vector closer to its actual meaning in the context. and then you get an output, which is another vector, and this kind of repeats itself in the second transformer layer. So you chain them one after another. But what happens inside every transformer layer is kind of similar. And the first part is, you want, like, what we are trying to do is we want to bring to, as I mentioned, we want to move the move the vector of the token closer to its meaning in that context that we provided. So the way this is achieved is, you want to bring in the context from you want to kind of understand from all the other tokens in the prompt what this token that we're looking at, like one particular one, means. And the way they achieve that is based on like a combination of three different vectors that are computed. It's you might have heard of them. It's query, like Q, K, and key, and then value as V and value. And the way this works is, for every token in the prompt, this pair of three vectors gets computed, and they mean three different things. The query vector means, okay, what information do I as a token need in order to understand my content, like to understand my meaning better? Like, what do I need from others? And the second one, the key is me as a token. And this, again, gets answered for every token in the prompt. The key is, the key vector represents me as a token. What context do I bring to others? Like, what's the meaning that I have for others? And then the value is based on the original definition of the word. Let's, from the dictionary, for example. If there are multiple ones, you might say, well, now I understand that for this KV, basically for this square and this key, the definition from the dictionary, because there are multiple ones, right, is this one, right? So basically the V vector kind of represents the meaning, the sub meaning of that word, of that token. So I'm using word and token interchangeable here, but I hope it's not confusing. Okay, so you have this tree that they get computed in by doing magic multiplication. So those are fixed for a token, right? So a token in an LLM model has these three vectors kind of fixed, as far as I understand. And now what happens is that you now start with your vector that describes what your word is, right? The thing that we start from the beginning. And now I'm saying this again. You want to move this vector into the direction of its meaning in the context. So now what we're doing is, for all the other tokens in the prompt, you compute, like, you basically take your vector, like your Q vector, meaning, okay, what context do I need as a token in order to understand myself? Like, I understand what's my actual meaning. So you're taking this vector and you're multiplying with the key from all the other tokens in the prompt. Remember, key means what context do I bring as a token, right? So you're multiplying the question, right, the Q yourself, with the key, like the context that other tokens are bringing. And you're doing that multiplication, which help you, like they help us understand how similar those two are. Like, how similar is what you're searching with what is provided, right? And you want a strong correlation between those two, because then it means that, oh, I found a key, meaning a different token, that kind of correlates with what I'm searching, that will help me better understand my meaning. Okay, so now what we want to do is we compute this dot product for a all the other tokens and myself. Like again, I'm speaking from the point of view of a single token, but this happens for all of them. And for a single token, you compute this dot product for with all the other um, keys of the tokens in the prompt. And now you want, remember the v vector kind of describes what the definition, like what the subset of the original vector, this kv combination, like qk combination, is hinting towards. So you're taking you're doing a weighted sum of those vectors. Basically what is going to happen is the vectors, like the definitions of those tokens in the prompt that strongly correlate and help understand the meaning of the token that we're processing, those definitions will kind of be more like they will be more impactful, right? Because their dot product sum is higher. Sorry, yes, their weight will be higher. Cool. So now we're summing all those things up, and I know this is going to get confusing because I'm not drawing this, but now we, by summing and doing this weighted sum, actually, we are kind of improving a bit the direction of the vector that we're processing, like the of our token. And that's the goal, right? We want to move it into the right direction based on the context. So what I describe now is called, I think it's called an attention head, and this happens. It's one block, but this actually happens a lot of times. Inside every transformer layer, it happens per token, maybe 96 times, or a lot of times. Because every attention head is trying to bring in and move the meaning of a token into the right direction, but from a different perspective, right? For example, one way to think about it is we want to clarify that the word that we're like that I'm that the token is part of, it's a verb, right? So it might, one attention head might kind of search for other keys, for other tokens that would tell it if it's a verb or if it's um, a noun, right? So that's one area, but then you have different ones or different perspectives, and every attention set is built or and trained in a training phase to be able to move the conversation into to move the token into that direction. Okay, so we start with the token that is 496, right? That got into a transformer layer, and then you get another vector that kind of takes it into inside the transform layer. You kind of moved it into the right direction based on this attention heads, and now it gets passed into a neural network that was trained to for building this prediction, right? So we took in the right direction of the token. We have a better meaning of it, but we still want to move it into being able to predict what the next word is, right? That's the goal. We want to a vector that helps us identify what the next word is. Cool. So you pass it into the neural network that was trained for this purpose of predicting the next word, and then the transformer layer finishes and it moves to the next transformer layer that is similar, but it has all this parameters are different, right? Okay, so now we're at this stage. You went into all the layers, and at the end, when it finishes the last transform layer, you again have this vector, right? That and you build it for all the tokens in the prompt. But now the thing is, we are actually looking only at the last token in the prompt to predict the next one. because that one already has built in the knowledge of what should come next, because of the way the attention set is built, and because due to the way all these transformer layers are built, like all the needed direction or details for identifying the next token is built into this vector that belongs to the last token. Everything else was only built to achieve, like to help building this one. Okay, so now we have this vector, and based on it, we want to predict the next token. And the way we do that is we do kind of check it against all the other tokens in the dictionary, the thing that I described at the beginning. And the way we do that is we multiply it. We multiply the vector by the dictionary, the token dictionary. And basically what that means is we're doing a dot product. Remember, the dot product of the two vectors help us understand how similar they are, like how similar in the sense that they are pointing in the right direction, in the same direction. And then you're doing a math function that kind of helps you sort them based on the dot product. And now there are different ways to decide which next token to choose. But let's say that we are choosing always the most probable next one, right? The first rated one. We're taking that one and we're saying, okay, this is the next token. And here's the interesting part. What happens now is that you generated this new token. It's one token, remember, but at most it's a word. This gets appended to the prompt, right, at the end, because you're now confident that this is the next one. And now the whole thing starts all over again. For every token up until the end of the output, the same thing gets repeated over and over again. And this is a massive amount of computation. I will mention one thing about this before closing, which is, even though this starts all over from the beginning, for every new token that gets appended to the prompt, internally, not all the computations are repeated, because a lot of those, remember those KV, like the key and the value, those vectors that got computed for all the tokens in the prompt, they get cached. So the first time they get computed in the what's called the prefill phase, the when this part, like when this runs first before generating any new token. So they get computed and they get cached, because when a new token comes in, it will, like, the way they make this work is that they don't look, this new token is not influencing the existing key and value of the tokens that got computed already, like that they are present in the token, right? They are already there. Like, remember, they are based on themselves, right? So they don't change. And like, remember when we said that for every token in the prompt we compute these three vectors, there's not in conjunction or in combination with something else. We are computing the dot product of the Q vector for a token and the K vector for a different token to figure out the context and how important that other token is. But we're not right. But these three vectors are independent one from another. Sorry, cross tokens, right? So when you hear a KV cache, it's because in the prefill phase in the beginning, for all the for all the tokens in the context, for all the tokens in the prompt, these KV values are built and stored, and they are kind of stored all until the computation finishes. I hope this helped you. I'll be happy to hear any comments if you have them. Thank you very much.